Thank you for attending today's workshop on BitVM, where we're going to build an app together, and you're going to learn a lot. So, you guys ready to get started? All right, awesome. So the first thing to do, I recommend, is you pull up this presentation. There's code in this presentation that we're going to be copy-pasting and working with. So I recommend you pull it up. You can do that by visiting tinyurl.com/bitvm workshop. And let me just show you what happens if you visit that URL. It's just going to pull up the same presentation that we're currently looking at. Presentationception, right? So yeah, that's pretty cool. I think I'm just going to leave that link for a few minutes in a new window. So I think I can do that with Notepad. You just put it right there, and we'll make that nice and small. And I'll just leave it up there for a few minutes so y'all can do that. Once you're on the webpage with me, the next thing I recommend you do is you visit these 3 links. So we got a GitHub link right here. This is the project we're going to build. And we're going to build tic-tac-toe together. So you can come to this link, and then if you click the URL over here, you can actually see the completed project. This is tic-tac-toe. And it works. You can actually play it. I'm going to do that just in a minute, but actually, you know what? Let's just do it right now. Let's play a little game. When you come on here, you got to open your browser console. So I'm opening mine, and I'm going to put it over on the left because I've got the URL up on the right. So you got to open up your browser console like I've got here. You can do that in Firefox with Control-Shift-I. On other browsers, you can do like menu, more tools, and you'll find it over here in like web developer tools. So that's a couple of different ways of getting there, but you need your console open because a lot of the code that we're going to use is going to be in here. 2 other things you need are the transaction broadcaster from MutinyNet. We're going to use that to broadcast transactions on one of Bitcoin's testnets. MutinyNet is a testnet, Bitcoin testnet created by some friends of mine. Anybody can spin up a testnet. Some friends of mine did, and they modified theirs so that blocks come in about every 30 seconds, which is great for testing purposes. On testnets, the coins don't matter, and you can adjust block speeds and other rules of the Bitcoin network. And then also, because the coins are fake and they don't really matter, they also created this little faucet where you can go and get some free coins. And so I use this all the time. I use it in this demo to simulate interacting with Bitcoin. Okay, so once we have that, let's click the play button and we'll see what happens. It asks us if we would like to send some money to this Bitcoin address. It gives us a nice little Bitcoin address right there and prompts us to send some money to it. And then enter the transaction ID. So I'm going to go over here to MutinyNet, just testing out this little app, see how it works. I'm going to paste it in. I'm going to send 10,000 sats to that address. And then I can actually view. I'm going to open that in a new tab. I can view the transaction in the mempool, in the testnet mempool. There's the transaction ID. And, oh, it just got confirmed. The beauty of having really fast blocks. So the thing says, please send money to this address and enter the transaction ID. Now, I know you're looking at this and you're thinking, what a horrifying user interface. This thing's asking people to copy paste things from other places, and it's just wacky. I know this is not a finished product, and this is not how you would play tic-tac-toe in real life. We'd be using an API to do all this copy pasting stuff. You'd be playing it on the real Bitcoin network. This is just to show you an overview of how you can make tic-tac-toe work. So the next thing it wants is a transaction ID, or a VOUT, I mean. So what's a VOUT? Well, every Bitcoin transaction has a from address, which is over here, one or more addresses you're sending money from, and then 2 addresses, like where you're sending money to. And in this case, the faucet sent most of the money in its wallet back to itself and sent just a little sliver of it, 10,000 sats, to us. So these 2 things over here are called VOUTs. This is VOUT 0, and this is VOUT 1. And VOUT 1 is the one that has our money in it. So we need to say to our little app here that VOUT 1 is the one that has our money in it, right? And then it wants to know the amount, which is 10,000 sats. That's how much we sent. Okay, so we've done that. And we got two conflicting instructions here. We've got one that says, please broadcast this transaction hex to start Alice's turn, and one that says, please place an X. We do this one first. We get a transaction here, and we start the game by broadcasting this transaction into the testnet. Give us a little transaction ID. Success. We've moved money on Bitcoin. Cool. Or on, a testnet. So we've done that, and then it wants us to place an X. It is X's turn to play. I'm just going to place an X in the top left corner. And then it says, reveal this move preimage to Bob and broadcast this transaction. So here's a longer transaction. This has actually got some of the rules of tic-tac-toe encoded in it. So let's go take a look. I'm going to broadcast this. Notice it's a larger transaction than the previous one. We'll take a look at it. All right, so this transaction pays 500 sat fee. It sends money from the starting address to this one over here. And if you look at the details, there's a few details in here. We have a witness stack that has two signatures on it. Those are the two players, X and 0. I call them Alice and Bob. Alice is X, Bob is 0. They're both playing, so both of their signatures are in here. We have something called a move preimage, which is Alice's way of revealing which X or Y or which position she picked on the board. And then down here, this code is enforcing one of the rules of tic-tac-toe. I'll show you this when we get into the code base a little later. And then this down here is a tap script thing. We're using tap script for this, and this tells us which tap leaf we're spending from. If all this doesn't make much sense to you, we'll get into it later. But yeah, you can actually play a game of tic-tac-toe right in here, and you just copy-paste stuff from your browser console to change turns. So now it's O's turn or Bob's turn, and he can place an O right there, for example. And he has to reveal two things to Alice and broadcast a transaction. And they do this back and forth 9 times to finish the game. All right, so that's what we're going to build. And let's get started. Let's actually get into it and make some things happen. Okay, so I want you to be aware that you should lower your expectations for this presentation. This is just a sneak preview of a code base that I'm still working on. As you may have noticed, it's not finished yet, and it's not very good. What I'm actually preparing this for is advancing Bitcoin, which is next week, and hopefully the code will be in a better state by then. But yeah, the code is not ready, and the code is very messy and long, 1,450 lines of code, which is longer than usual for me in these types of presentations, and it's also a mess, as we'll get into later. I stayed up until 5:30 a.m. working on this presentation. It's currently 9:30 a.m., so I got 3 hours of sleep last night. So that's another reason to lower your expectations and don't expect too much. But we are going to learn some stuff. What are we going to learn? Well, I think I can get rid of this now. Hopefully you're all with me at BitVM/workshop. First, we're going to learn how to build tic-tac-toe. We're going to build that thing you just saw. We're going to learn how to use BitVM to add rules to Bitcoin script, like the rules of tic-tac-toe, so that it can actually evaluate whether some logic is true or false. Bitcoin doesn't know the rules of tic-tac-toe, so we've got to teach it. We've got to add the rules of tic-tac-toe to a set of Bitcoin transactions. And hopefully from this, you'll learn that not only can you do tic-tac-toe, you can do any logic. Like BitVM supports any computable function. So we're going to show you that. We're going to learn how to transfer state from one transaction to another. We need to do this in tic-tac-toe because trying to encode all of the rules of tic-tac-toe in one transaction would be too large. So we do it in multiple. And that's a feature of BitVM. We're going to learn about guard tap leaves. That is one of the things you need to do in order to transfer state in BitVM. I'll show you that in a little bit. And we're going to learn how to prove fraud. There are ways to cheat in tic-tac-toe, or try to, and we're going to detect those and take someone's money if they try to cheat. Sound good? Things you will not learn, and these are part of lowering your expectations. Some of you may be watching this and hoping to learn how to use an existing BitVM code base. I've written a lot of existing code for BitVM. So has Robin Linus and his team, who invented BitVM. They've made a lot of code for this. Unfortunately, the code bases we've created are not designed for two-player games. I made an 8-bit computer, which is certainly capable of running tic-tac-toe. However, it's not designed to let two players have the controls. It's designed for, we call them Paul and Vicky. It's designed for Paul and Vicky to agree on a program to run, and then Paul has full control over it, where Vicky just checks that he does the computation correctly. In tic-tac-toe, they both need to have a hand on the controls. In fact, they both need to act as prover and verifier, proving that they're following the rules and then verifying that the other player's following the rules. Neither my code base nor Robin's are designed for that, so I had to start from scratch in order to build this. So this is kind of cool. Not only are you building tic-tac-toe, you're also building the virtual machine that it's going to run in, which is neat. We're not going to be able to call any BitVM libraries because none are ready. Robin has a library that's very nearly ready, but it's not, so I couldn't use it. And we're also not going to be emulating a CPU because there's no need for a strong, even an 8-bit CPU is overpowered for tic-tac-toe. You're really just checking whether things have been revealed. So yeah, we don't need a CPU and we're not going to be emulating one. If you hope to come into this presentation learning to use an existing BitVM code base, learning to call the BitVM library, or wanting to see what these CPUs are like and how to develop on those, my apologies. That's not what we're doing today. Lower those expectations. Keep them down. Just building tic-tac-toe, my friends. I wish that a BitVM library did exist that had the following properties. I hope to make this, or maybe one of you watching or one of you in our audience can build this for us. I wish that we had a library that automatically created user objects for Alice and Bob, keeping track of the state as they reveal the game board and add pieces to it. I really wish that a library existed that had methods for creating a series of transactions automatically, where you send things back and forth. You just say, all right, Alice has to reveal this, and then Bob has to do this, and then they have to validate that. It would be really cool if we could just call methods to do that. Unfortunately, that doesn't exist. So hope perhaps some of the code I've written here, will contribute to the eventually that existing, but we're not there yet. All right, enough introductory material. Let's get into actually building the code base. One further thing, I have not given an overview in this presentation of what BitVM is capable of. I hope that if you're interested in that, you go visit my previous videos. If you want a high-level overview of what BitVM can do, I've made videos in the past about it. Go check them out. I've done presentations at conferences. They're all on my YouTube channel. So go search my YouTube channel for BitVM for that. And this is like hands and guts. We're going to be doing surgery on some code to make it work. So that's what this is. The closest you're going to get to an overview is that BitVM can do these 4 things. So that's what we're going to be doing. All right, let's get started by creating a new file. I'm going to create a new folder called, what are we going to call this? How about bit-tac-toe demo? I will create a new folder called bit-tac-toe demo right there. And I'm going to go inside it and create a new document called, my favorite thing to call HTML files, index.html. Why do I call them that? Because if you upload them to a server, they look nice. It like shortens it and stuff, and it looks pretty. All right, so we've got a new folder, new document pulled up here. This is where the code base for BitVM is going to go. And the next thing we need to do is copy paste the code from our slideshow into it. All right, copy this, paste it, make this bigger so you can see. And all this is doing is it's going to create a little welcome to tic-tac-toe display with a play button and a box that has nothing in it yet. But let's open it up in our browser. And as you can see, there's nothing much in here as of yet. We've got a play button that doesn't do anything, except I think it'll probably throw an error. Yeah, there's an error because it's trying to call a function we haven't defined yet. And that's all we got, but it's a start. The next thing we're going to do is we're going to add the game board to this thing. We're going to insert the game board where it says tic-tac box. You just paste the game board into there. This creates 3 columns. Tic-tac-toe has 3 columns, and then it creates 9 squares inside those columns that we're going to add X's and O's to. Save that. If we refresh our page, it shouldn't look any different because we haven't given any style to the game board, so it doesn't show up. But let's do that. let's create a style tag. So I'm just going to go up to my head tag and replace this line that says viewport with this new one. Adjust the tabbing here so it looks nice. And this is just a little bit of basic CSS that's going to give our game board some lines so we can see what we're working with. Still, these buttons don't do anything. We haven't defined any functions. When you click anything, nothing happens. But hey, we got a game board now. You can see it. You guys with me? Cool. Next thing we're going to do is we're going to add some dependencies. So we're going to use a few files. Let's copy them and paste them in. Just replace this viewport tag with the new one. And let's view, let me tell you about these dependencies. The first one up here is called TapScript. This is a library for working in JavaScript with taproot transactions. So I'm going to teach you a little bit about how to use taproot today because it's needed for BitVM. Then we've got Noble SecP256K1. This is designed for creating and public keys and validating signatures on Bitcoin's elliptic curve, as well as private keys. It's got functions for that. We've got RMD160. This is one of the hashing functions Bitcoin supports. Hashing is really important in BitVM, and this is also the smallest one Bitcoin has, so we use this one to save on transaction sizes and make them smaller. And then we've got something called combinations. How many of you have taken a statistics course? Yeah, there we go. And do you know what combinatorics is? If you do, hang on, because we're going to get into some combinatorics. Let me show you what combinatorics does, because we're going to use it a little later. If you have a set of 4 elements and you use combinatorics, you can run a function called for_choose_2, and it will give you every combination of 2 elements that are from this set with no repeats. So you got AB, AC, AD, no repeats there. It's not going to give us AA because that would be a repeat. And we've got BC and BD, and BA is already included, so it doesn't include it again. And then we've got CD, and we don't need to include CB because it's already right there, and we don't need to include CA because it's already right there. But yeah, this is all the sets of elements you can get from 4. I think I didn't actually check. I just sort of did it by eye. But that's all the elements that I think you can get with for_choose_2 from a set of 4 elements. This is combinatorics. This is going to blow up our transaction size. Maybe try display resolution again. Okay. All right, I updated the display resolution. Did that fix it? Well, I've got a local recording, so we can use that. That'll have everything on it. So for you guys just watching, just use the PowerPoint for now, and we'll upload the slideshow later. Sound good, Lucas? Technical issues, folks. Sorry about that. Yeah. So this is where we're at, and you guys can of course follow along by viewing what's on here and then following along with the presentation because you guys have a link to it. So we should be good. Share the link again. All right. The link is tinyurl.com/bitvm-workshop. So go there to follow along, and then you'll have the presentation right in front of you. You can see what's on the screen, and then follow along with it on your own computer. All right, great. So let's keep going. So that's combinatorics. We're going to use that. That's going to blow up the size of our Bitcoin addresses. All right. So the next thing we need is a few more dependencies. These ones, we're going to plop them here under the dollar sign thing. These are functions for they're taken from like the jQuery library. They let you grab elements in your web page and modify things very easily in a syntax that I appreciate. So we're going to add these. Hex to bytes and bytes to hex are functions for dealing with raw byte strings. JavaScript likes raw byte strings to be in this format it has called uint832, and then Bitcoin likes them to be in hex format, so we have to convert between those two. This is the RMD or RIPEMD160 hash function. I wrote a little wrapper for it that makes it compatible with how we're going to use it. And wait a sec is a really cool function in JavaScript that makes your computer wait. It makes it wait a second, or however many seconds you specify. And I use that later for watching whether it's your turn or not. If it's not your turn, you just kind of cycle through a set of numbers and waiting until it's your turn. So that's what that does. Those are some dependencies. Every now and then I like to save and refresh my page and make sure that I don't see any red errors. If you have an error in JavaScript, at least in Firefox, it'll show up as a little red um, text right there. Good thing we don't have any errors right now, so we can keep going. All right, the next thing we're going to do is make our box, our tic-tac-toe box, do something. So we're going to place a new script. We can just place it right under our previous one. And this is just going to create a type, whether we're X's or zeros. X's are represented by ones, O's are by zeros. It's going to create the number thing that lets us wait for our turn. And then it's going to create a variable called game on. If we set game on to true, which we're going to do later, then the game board will be live and we'll be able to draw X's and O's in it. So if we refresh our page, we can't do anything because the game board's not live. But if we do game on equals true, now didn't work. Oh no. Well, I thought it was going to let us draw on the board, but it's not. So what did I do wrong here? If game on is return, so console log game on, refresh. So it is not recognizing that I am clicking a square. So let's try this. Interesting. Maybe I got to do like that, and then it'll be happy. No, it's still not working. Anyone see what I'm doing wrong here? Huh?
Mine is working.
Yours is working, huh?
Yeah, I did game on through and then I click it and there's an X. So I just copy and paste what you did there.
So if I do this, so now mine is working, which is weird. So somehow it is not recognizing that I've added this code to it, and I'm not sure why. Let me try doing that, putting it in a different script tag. I don't think this is going to work, but it is not good that mine is not working. Game on equals true. Still not working. I'm not sure what to do here. Let me go to my GitHub where I do have a working copy of the code. I must have copy pasted something incorrectly. So I will go to BitVM workshop, and I will copy the code from there into my HTML file, and then erase everything we haven't done yet. Paste all that, and then go down to the bottom, erased all this stuff. This is our 1,400 lines of code we'll be getting to as soon as I can. So I don't need any of those. I just need to go all the way up to where the game board is. Those combinations. There we go. So now I should be in the same place we are. And if I refresh and do game on equals true, now it's working for me. So I must have copy pasted something wrong. Hopefully we're all on the same page. Do you all have a working game board on here? Okay, sweet. Crisis averted. Next thing we're going to do is we're going to start creating some global variables that we're going to use for storing state in JavaScript that will eventually be represented on Bitcoin. So I'm just going to go down here and paste this script tag. And so what do we got in here? Well, we've got something called contract that is an object that's going to eventually have a bunch of transactions in it. And each transaction is going to send money through something called a dependency chain, which I'll get to later. We've got a set of hashes that we're going to reveal as we play this game. We're going to reveal pre-images to hashes, and those are going to represent updating the game board. We're going to keep track of whether fraud has occurred and whether victory has been achieved by either party. If it does, then it stops the game and lets you take the money, take your winnings, or take your reward for finding fraud. Then we create Alice. She gets a private key. Hers is not a very secure private key. It's just the letters AB repeated 32 times. You can, of course, if you were doing this for real, you'd give her like a real serious private key. She has a bunch of stuff in here for keeping track of her state, as well as the scripts she's using, things called accept preimages and accept hashes, which are her way of acknowledging Bob's moves. And I'll show you how those work in a little bit. The next thing we do is we continue adding. We need to keep track of Alice's. Well, we need to give Alice a pub key. She can't just have a private key. She also needs a pub key. So we use the noble secp library for that. We create a funding address, which we're going to deposit money to in a little bit. And we keep track of Alice's latest pre-image hash and move right here. I mentioned the code is ugly and long. You're getting a sense of that here. And we are not nearly through it yet. But we're going to keep going. And we're going to do the same for Bob. Bob gets all the same thing Alice does. He gets private key. He gets ways to track his state. He gets a public key, and then we get to keep track of his latest pre-image hash and move. So those are some stuff. Let us refresh our page and make sure there are no errors. I don't see any. Great. So we've got Alice and Bob created on here, and this is one thing. I think it'd be really easy to create a library that did this part because it's really just creating a bunch of objects, and that's super easy. And that would be helpful. Like just doing that ahead of time would already be a helpful start. So one of you out there who was watching, go and make a BitVM library that does that, and then we'll have a starting point for making something really cool. The next thing we're going to do is we're going to create pre-images for Alice. So I'm going to paste the code, and then we're going to discuss it. All right, so what do these pre-images do? Well, first, let's see that it's working. If we look at Alice right now without refreshing the page, alice.preimages is an empty array. So you can see over here, it says array, and then there's nothing in it. Well, now let's refresh the page. And when we go and check Alice preimages, now she's got 45 preimages, which is 9 times 5. So it creates 45 preimages for her and 45 hashes and adds them to her preimages array and her hashes array. Now, why do we create 45 preimages? The number 9 here should give you a clue. Anyone have any guesses why the number 9 is in here for the number of preimages she has? That's right, because there are 9 things on a 9 cells on a tic-tac-toe board. So basically, what we do is we're going to tell you why there's 9 times 5 here. On every turn, either Alice or Bob is going to place a mark. Alice places an X on turn 1. She places another X on turn 3. And as we keep going, there are 9 squares, and Alice gets 5 turns. She places an X here, 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 and here, and finally she wins in this board, right? So she gets 5 times to place one of 9 marks on the board, and basically we're going to reveal a pre-image for whichever one she does. So we create 9 copies of 9 pre-images to represent each one of these cells, and she's going to reveal one of them per turn to represent where she's placing her mark. Now, some of you may be looking at this and saying, well, this one's no longer available. You could have made it 9 times 8 times, 9 factorial instead of what I did. And yeah, I could have done it in a more efficient way. Actually, I don't think 9 factorial is the right math, but whatever. I could have done this in a more efficient way, but I didn't because I want to show you fraud. I could have made it so she can't commit fraud, but I want her to commit fraud so I can show you how to handle that in BitVM. So she's going to be able to commit fraud either by overwriting existing squares or by like taking a turn twice and some other things. So that's why we're doing that. And also, if you notice that Alice has 5 turns and there are 9 positions on the board, how many turns does Bob get? Any guesses? He only gets 4. He places a circle here, 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 and here, and he only gets 4 turns. So he doesn't need to create 45 preimages. He just needs to create 36. Tic-tac-toe sort of favors Alice. It favors whoever's X. Okay, so let me just add him to the board. So now Bob can create preimages and hashes as well. And then we need to do something called acknowledgements. We use these later. There's a place in the code where I need them to acknowledge each other's moves in order to proceed. And so Alice creates 36 preimages and hashes to accept whatever moves Bob has made. She has to, like, if he reveals that he took square 2, she has to reveal the corresponding one for square 2 on his turn. And the same thing for Bob. He has to create 45 preimages so that he can acknowledge all of Alice's moves. And so he does that right there. Save. Let's go back and refresh our code, make sure there are no errors. That's good. And now we should have Alice.accept preimages and accept hashes should both have things in them. Similarly for Bob, accept preimages should now have 45 hashes, 45 preimages, and he does. So we're good. No errors so far. Everybody with me? Cool. We are into it. We're getting into the guts of this thing, and it's going to get messier and messier as we proceed. So the next thing we're going to do, when I put up those prompts, it always covers the board, and I can't see what's on it. So I also have a copy of the board in my console. And so we're just going to create a little set of script tags here that put a copy of the game board in our console, and then we'll log it. So if I refresh, now we've got a copy of the game board right here, and we've got those prompts. We can still see what's going on. Not strictly necessary. If I want, maybe I'll remove that someday, if I like get rid of the prompts or something. But here it's helpful. All right. Next thing we're going to do is create yet another script tag, and we're going to create some test scripts that show us how taproot works. So what I wanted to do here initially when I was preparing this is I wanted to have Alice take her first turn. But it involves creating a set of tap leaves, and I thought most people haven't worked with taproot before, and they actually don't know how taproot works. So I thought we'll do a test transaction on taproot just so you can see how this crazy taproot upgrade works. So I'm creating in taproot. You create a Bitcoin address that has multiple ways of spending your money. In this case, I'm creating an array of scripts that we can use to spend our money, and there are 2 scripts in it. One here, one here. So script 1 is essentially a hash lock. It says you have to supply a preimage, which we're going to hash using the ripemd160 function. We're going to compare it to this hash right here, and check if the preimage you supplied hashes to that value. If it does, Alice can spend the money, but we're just going to check her signature. The other way you can spend it is using a time lock. We could say if 3 blocks go by and Alice hasn't spent the money, then Bob is allowed to spend it. So we have 2 scripts in here, and if we save this, let me go back to our code because we have more things to do here. It's going to create a tap tree, which is a list of all of these tap scripts, and it's going to create a test public key. In Taproot, whenever you have a script path that you're going to spend with, Taproot also lets you have like a backup public key that can spend the money if no one can spend using the scripts. In this case, we don't want to use it, so I'm just setting the public key to be AB repeated 32 times. And there is no private key to this address, so that means it can't spend the money, and that means we have to spend it using one of these scripts. You can do that if you have a situation where you only want the script path to be spent and you don't want the backup public key method. So then we get a tweaked public key, which hashes these scripts and then multiplies them by this test public key to create the Bitcoin address we're going to use. And then we just log it. We log the address and say, hey, send some money to it. So that's what that does. The next thing we're going to do is we're going to create a transaction. And the transaction is going to say, hey, we sent money into this address in this transaction. Here's the transaction ID. This is the V out for it because we have to specify that in Bitcoin. And this is the amount we sent, and this is the address we sent the money to. So that tells Bitcoin this is where we're sending our money out of. Then we're going to say this is where we're sending the money to. We're going to send it to this testnet address. This happens to be the faucet's address. So we're sending money back to the faucet. And then all we got to do is run this code. To finish it off. So this says which script we're going to spend using. We're going to spend using the first script, the one that says we have to reveal a pre-image. We're going to sign using Alice's private key. We're going to sign this whole transaction. Input 1, there's only one input, or input 0, I should say, so index from 0. And we specify a target. So this target thing is a hash of the script we're using. So it hashes that script and says, here's the script we're going to use. Then we get something called a control block. We have to prove that the hash of this script is committed to inside of this Bitcoin address. And that's what the control block does. So we get the control block. That's the last thing that goes in the witness stack. We add them both to the witness stack along with our pre-image, which happens to be the number 5, is the pre-image that produces this hash up here. And then we create a transaction and log it. So let's do that. It says, please send some money to this address. So we can do that using our little faucet. Start over. We'll send 10,000 sats to it. Paste. Let's check it out. It wants the transaction ID. There it is. The V out happens to be 1 in this case. So we'll say, here's the transaction ID. The V out is 1. On yours, it might be different. Check what you're doing to see. How much did we send? We sent 10,000 sats. And then it creates a transaction for us. It says, here you go. You should be able to broadcast this and send the money straight back to the faucet. Great. So if that worked for you, you are now one of the few and proud who have used Taproot for something, for a demo. And also, I wanted to mention that if we want to, we can change this to use the other script. So all we got to do is say, to do that, is we can change to using script 1 instead of script 0. And same thing down here, we got to say we're going to use script 1. We don't need the pre-image anymore because it doesn't require one. So we can get rid of that. And I think there's one other thing we need to do. I'm not sure if there's anything else. Oh yeah, we need to change to Bob because Bob needs to sign if he's spending instead of Alice. So Bob's signature is needed on the stack. So yeah, this should work. If we refresh, we should be able to do the same thing again. And you'll notice the Bitcoin address is the same. See how it ends in ZDJW? And that is the same Bitcoin address that we used right here. It sent money from ZVDJW. So the Bitcoin address is the same, but we're using a different script now to spend from it. So let's send some money to it. Send 10,000 sats. I don't know why MutinyNet is struggling now. All of a sudden, it's like the internet went out. Hey, Lucas, is the internet okay? Well, there, now it worked. Hopefully it won't be like that the whole time. But if I copy this, it wants to know, this time it's 0, our V out is 0. So I'm going to paste the TX ID, V out 0, we sent 10,000 sats again, and now we've got a new transaction spending using Bob's signature instead of Alice's from the same address, and broadcast it, and it failed. Oh, the lock time's not satisfied, of course. So, what? I don't have a port for that. So this one requires a lock time to pass, right? We need three blocks to go by. So if we look at the transaction where we deposited this, only one block has gone by. So in 2 more, we'll be able to do this. But I did forget that when you use check sequence verify, you have to add a sequence number over here. And sequence number 3 is the one that we require. This tells Bitcoin you have to wait for 3 blocks to go by before you can spend this money. So I forgot to do that. So when 3 blocks do go by, the transaction ID we created won't work because our transaction didn't say that. In fact, if I paste it now, we still get that error, lock time requirement not satisfied. But if I refresh and do this again, our TX ID is this, and I think our V out was, or not that one. Our TX ID was, I forget. Well, for you guys, it should work. I forget what the transaction ID was that we for depositing into that address. But yeah, it actually, I'm just going to redo it. Copy this, go to MutinyNet, start over, 10,000 cents, paste it. This is good practice for what we're going to do in a few minutes. Copy this, and the vout is 1. Paste 1, 10,000 cents. Here's our new transaction ID, spending using the other one. Of course, it's still going to say you have to wait for the 3 blocks to pass. Actually, you only have to wait for 2 because where's the one I just did? This is the one. You only have to wait for 2 because once 2 go by, it's allowed into the mempool so that it can be in the next block. So in about 30 more seconds, we'll be able to broadcast it and it'll accept it into that block. Yeah, now we can. And it'll be happy. Say, it's not happy. Well, I don't know what I did wrong there. It worked yesterday, but I'm going to move on because this is only a test anyway. Point is, you need to be able to have multiple scripts and use them. Try one more time. Yeah, didn't work. Okay, keep that open. We do need the broadcaster. Let's clean up all this stuff. Don't need that anymore. Oh, there it worked. Now it's happy. Enough blocks went by and it's happy now. So there's our transaction. Great, code works. So that was just a test so that you can see how taproot works. We're not actually going to use this code in our code base. It's just an example. We have other scripts that we're going to use. So the next thing we do is let Alice take her first turn. I'm about to show you how we do that, how we encode Alice's first turn, but I need to tell you about state transfer and tap leaf guards because the transaction, or the code in which she does this uses these things, and I haven't told you what they are yet, so you'll be super confused. Basically, we can't let this happen. Let's suppose that in Alice's first turn, she puts an X here, and then Bob, he's a smart guy. He takes the middle square, which is always what you should do if you're a second player, in Super's opinion. And so Alice, on her third turn, takes this one right here. But then later, it doesn't matter where Bob goes next. Alice's next turn, she says, aha, on my second turn, I actually put the thing here. And now on my third turn, I'm revealing that spot. We don't want to allow this situation to happen because then she's got 3 in a row and she's just lying about where she put her piece. So to prevent that, we use something called a tap leaf guard. We basically have 9 when it's either player's turn to move, they have 9 squares, or they have 9 tap leaves, in which they can select what their move is. And these squares are all identical, except that they start with a hash lock that is basically the pre-image from the previous player's move. Whatever, so if Alice picked this square in her first turn, when it's Bob's turn to play, he has to use tap leaf 1, and he has to reveal whatever pre-image she revealed here so that he can make his move. And that's his way of acknowledging, I understand and acknowledge that she has this piece. Similarly, when she does her move, she has to acknowledge whatever move he made. That's called a tap leaf guard. This is an invention of Robin Linus, who figured out that you can use this to let someone else pick what tap leaf you can use by having them reveal a secret for it. Then what I do is when Alice makes her winning move, she can't just do 3 in a row of her own revelation. She has to prove that Bob acknowledged 2 of those pieces. And by doing that, it prevents this situation. She can no longer say, I took this spot if Bob didn't acknowledge it. So yeah, that's what we're going to use tap leaf guards for. And this is called state transfer. When we have Alice reveal some information, which Bob uses in his script, that's transferring the state of the board. Like now they agree, once he makes his move, they agree that she has this spot. And then they agree subsequently that he has this spot. We're actually updating the state of the board as we proceed in through this game. So that is why when we start taking Alice's turn here, the first thing you're going to see, well, is not the tap leaf guards, actually. The first thing you're going to see on here is this weird code that I had to write for reasons which I don't want to get into right now. But we see 2 scripts, and they're pretty similar to the ones we just did. This one is a multisig. It says there's a happy path where Alice and Bob agree on the outcome of the game, and at any point they can stop playing the game and just say, yeah, I acknowledge Alice won or Bob won, and cosign using this to allow that person to win. How this script works is it's got a 0 over here. It starts out saying 0 public keys have been validated, 0 signatures have been validated. We drop Alice's pub key on the stack and check her signature. If it works, check sig add will increment this to the number 1. And then we check Bob's signature on his public key and do the same thing. It'll increment this to the number 2 if it's valid. And then we just check if there are 2, if our little number is equal to 2, that means both of them agreed on how to spend this money. So this is standard multisig in TapScript. That's how it looks. And then we've got a 10 block check sequence verify. If Alice, if it's her turn and she abandons the game, she's like, I'm not playing anymore. After 10 blocks, Bob can just take the money. So that's what those two scripts do. They're a little bit similar to the ones we did before, except there's no hash lock here. The next one is the one that has the hash lock, or the tap leaf guard in it. So on Alice's first turn, Bob hasn't taken a turn, so she doesn't have to acknowledge anything. So her pre-image is just blank, and we take the hash of an empty set is this. So that's her tap leaf guard. And then so she has to accept, that Bob made no move at all for her first turn. And I did that so that I can reuse this code. I don't have to make the scripts different for each turn. I can have her just reuse this code, and every turn it'll either be whatever Bob's latest move is, or if he didn't make a move, which means it's the first turn, then she'll just use blank as her tap leaf guard, and that'll let her make a move without needing to know in advance something from Bob. The next thing we do is we create this script right here. And so basically, so you'll notice that I'm making the same script 9 times. So for every one of her turns, she's going to get 9 ways of making a move. And in each one, she has to say which move Bob made in his previous turn. So that's what the script says. She has to accept what move Bob made. And first she reveals what preimage he used to make his move, and then she accepts that. She says, all right, here's a corresponding preimage where I acknowledge your move. That's why she has 36 accept preimages, so she can acknowledge every one of his moves no matter where it goes. And then she makes her move. She says, all right, here's the preimage to the hash I'm revealing for my move. And this is going to be one of 9 preimages for each one of her turns. So that's what that does. Then, look at this. This is just the worst code anybody's ever written. But here we go. So she reveals which preimage she's revealing to take her move. Then we just drop it from the stack because we don't need it anymore. We'd validate that the preimage she revealed is one of the 9 preimages she's allowed to make on each one of her turns. And if it is, then we use multisig. It's the same as the multisig from above, to say, all right, now it has to go into the next Bitcoin address, and they have to agree where it should go next. And that's how we enforce that the money has to go through a series of transactions that they both agree on in BitVM. So Alice's tree currently has 11 leaves. She's got the happy path and the abandonment path, where she just leaves the game, or they agree on what happens. And then she's got 9 paths where she can pick a square and say, this is where my next move is. And you might think her turn's done. She can move now. But you'd be wrong, because on each of her turns, she also has to be able to prove fraud or victory. She has to prove either that she has to have an opportunity to say, here's proof that Bob cheated, so I should get his money, or here's proof that I won, so I should get the money. So yeah, that is where combinatorics comes in. And this is where it's going to really blow up the size of our scripts. So we're going to copy in this combinatorics code. And for every combination, or for every, so what she does, she gets a list of Bob's hashes, and she's going to create a combination where for every 2 hashes, so Bob's got 9 moves that he can make in his first play, right? So we get the first 9 preimages that he can reveal, the first 9 hashes, and we say if he reveals 2 of them, if he reveals 2 moves on the same turn, that's a form of cheating. It's called taking a move twice, or trying to take 2 moves in one turn. And so if he reveals 2 preimages from the same set of 9, we put them on the stack, and we say if Alice knows both of them, she can spend the money because Bob tried to cheat. Does that make sense? This is going to blow up the size of our script, though, because combinations do this thing. We've got choose 2 of 9, and it's a lot bigger than the 4 we did earlier. So that's what that one does. The next one's pretty similar. This is for if Bob tries to skip a turn. I don't know why you would do this in tic-tac-toe. It just gives your opponent an advantage. But you could overwrite an X that you or an O that you previously wrote. And so this does the same thing as the previous one, except for the hashes, we're checking if this one is 0, this one's going to be 9 because those correspond to square number 1 on 2 different turns. 0 through 8 are the preimages he can reveal for his first turn, and then 9 through 18 are the preimages he can reveal for his second turn. So if he reveals the same square on 2 different turns, that's him overwriting one of his squares. And it's a stupid thing to do in tic-tac-toe, but it's against the rules, so I have to account for it and make sure he can't do that. And then we just check if she knows both of those. If she knows 2 preimages by him for the same square, she gets to take the money because he tried to cheat by overwriting himself. The other thing you can do is he can overwrite Alice. He can say, you know what? I want the middle square, and Alice took it, so I'm just going to put a 0 there as well. So to check that, we basically check that he already revealed that an accept hash, an accept preimage for the middle square, and then he revealed that he's taking the middle square. So if he reveals 2 of those preimages, then she can just take his money. We do the same thing. We check that she knows both preimages, and if she does, that means he tried to cheat by overwriting one of her squares. So she gets to take the money. So that's what those 3 pieces of code do. That's how she proves fraud. Our script now is really big. Like the number of tap leaves we have due to all these combinations is something like 540. We have like 540 tap leaves in here. And this next one is for Alice claiming that she has won. And it's really complicated. Let's paste it in and see what it looks like. Okay, so what does this do? Well, it creates a set of an empty array of combinations. And for each of the 9 so we got a grid of 9 squares, right? And on the top row, Alice can win in one of 3 ways. She can either have square 0 and square 1 that Bob acknowledged she already has, and then she reveals that she also has square 3, or square 2, I mean. So 0, 1, and 2, that would be the top row. Or in the top row, she can have 0 and 2 already that Bob already acknowledged, and then she can reveal she has the middle one. Or she can have the 2 last ones, and then she reveals she has the first one. So for each of these things, we get not only 0 and 1, but also every offset, because she might have gotten them on a subsequent turn. So this square 9, preimage 9, is equivalent to preimage 0, but on her second turn, right? Preimage 18 is equivalent to preimage 0, but for her third turn and her fourth turn. So she can reveal any combination of these things. But what do we do down here? This is ridiculous. If they're too close, we don't accept them, because that means she's doing it on the same turn. So she can't have gotten both 0 and 1 from him, because that would mean she took the same turn twice. So we don't acknowledge that she can do that. And similarly, if they are a multiple of 9 apart, that would mean she took square 1 on turn 1, and then she took square 1 on turn 2, or 3 or 4, and we don't allow that either. So we get rid of all those, and this allows her, in any row of the board, if she can prove she has 3 on a row, 2 of them being acknowledged by Bob, she can win. So that's how she claims victory. But if you think we're done, we are not. Oh, this is me explaining that with diagram. Look, I did it. There's 3 ways to win in the first row, and she has to pick one of them, and the same for the second row and same for the third row. Okay, so for each of these things, if you think we're done because now she has a way to win for every row, we're not done, because there are 5 ways for her to win on every row. She has 5 different turns, and she could reveal, let's say that she's doing this one, and Bob acknowledges that she has 0 and 1. On any of her 5 turns, she could reveal the third X, right? In the top row. So there's 5 different ways for her to do that. So for each of these things where she's got, 0 and 1, we need to make 5 copies of it so we can insert the 5 different ways so you can get the third box. So that's what's down here. It increments it by 5 for each combination here. We're blowing up into like 900 tap leaves here just for one turn of Alice. And this, I'm not even going to apologize for the ugliness of this code. But what it's doing, I'm going to put it into a prettify JavaScript so I can explain it better. Prettify JS, online JavaScript beautifier, paste it, beautify it. So this makes it a little bit easier to read. So if she's got 0 and 1, it allows her to win if she reveals preimage 2 or preimage 11 or preimage 20 or preimage 29 or 38. Those are all the third square in each of her 5 turns. And the same for the bottom, for the next row, it just keeps doing that. So for every way that she can win, it gives her 5 ways she can win, depending on which turn she's using it on. And this if index is less than 180 thing, that's for all the tap leaves that happen to correspond to the first row. Then there's a lot more. So we're up to way many tap leaves now. But we got to copy this, paste it, and we got to do that 3 times for each of the rows that she can win in. So yeah, there's one, and then the third one is right here. So that allows her to claim victory. And if you think we're done, we're not yet. We haven't even put the preimages in. We just got the numbers of her preimages into this combination thing. So for every combination now, we go through and we swap out the number for the corresponding hash so that she can reveal that preimage, either one of Bob's accept preimages or her own revelation preimage for taking that square. And we paste it. And now I think we're done. Are we done? Oh, no, we're not done. We got to encode this. We got to take all of her 900 some tap leaves, encode them as hashes, and then make a tap tree so that we can say she can spend using any one of these paths on her turn, either by making a move, proving Bob committed fraud in one of 3 ways, or by showing that she's actually won the game. So we paste that. Make sure our indentation is correct. This is supposed to be an end script. Let me fix that in the board here. And we can test if it works. So we can save and refresh our page. And after all of that, our payoff should be that if we run this little piece of code, it should give us Alice's first, not there. It should give us Alice's first address. And there it is. All of those 900 some tap leaves, which we can actually view if we go to alice.scripts, there are 921 different ways that she can spend on each of her turns. So now you've seen what it's like to develop in BitVM. And this is why I'm only aware of 7 people in the whole world who've actually made something that runs in BitVM. Because this is what it's like. It's very low-level programming. Robin's team is trying to create abstractions on top of this so that you don't have to deal with combinatorics and stuff. You just like call a function and say Alice has to reveal a number 0 through 9, and then it'll handle the rest. But these libraries aren't ready yet, and that's why we're doing it the hard way in here. So most of our script is done. We have actually learned all 5 things that we said we're going to learn. We've learned how to do state transfer. We've learned how to do multi-party computation. We've learned how to do tap leaf guards. We've learned how to prove fraud. And I forget what the 5th one was, but we learned that too. But we're not done yet. The game doesn't actually work. We can just take 1 turn. So for the next thing, the rest of this should go pretty quickly. We just do the exact same thing for Bob. So I'm just copy pasting the same script in here for Bob. It's slightly different. Like he has only 4 turns, so he has a fewer number of combinations that he can do. He can't win 5 different ways. He can only win 4 different ways. And consequently, his number is not 180 up here. It's 144 instead. And there's a little comment here that explains why that is. But yeah, it's mostly the same code, so I'm not going to go through and explain it all again. But that he does the same thing she does. Every turn he gets that. He gets to do he gets to pick one of, almost 900 different ways to spend the money. And you might think we're done, but we're not. We still have to. We have code in their tap leaves for Alice or Bob now to prove the other one committed fraud. But they have to actually be able to detect that. Like when they're playing the game and we're revealing preimages to each other, the JavaScript has to be able to detect which of these tap leaves they should use to prove the fraud or to claim victory. So that's what this thing does. This is a function called prove double turn. And if we pass it 2 preimages, it will check if there's any tap leaf we can use to take our opponent's money. So that's what this one's going to do. We just paste it in here. It has 3 sections. And the code is almost identical to the code that is in the actual tap leaf, except now we're doing it in JavaScript. So there's that one. And there are two other ways that Bob can commit fraud. He can take two turns in a row. He can overwrite himself, or he can overwrite Alice. So this one over here called prove overwrite self. No, not. We grab it, and I'm just going to stick it into the same script tag. So it's the same code as we already saw, but now just making it so we can detect this in JavaScript. So that's that. And then we've got another one. He can prove that Alice can prove that Bob overwrote her, or Bob can prove that Alice overwrote him. So we do that with prove overwrite opponent. The code is the same as the code we've already seen. So it's this gigantic mess that we've already looked at, and I explained it with the prettify function. But now, if JavaScript detects it happened, it's going to set the fraud occurred flag, and it's going to let Alice spend the money. Or vice versa. If Alice does it, then it'll let Bob spend the money. So there's that. And now the three ways they can commit fraud are detectable by just revealing preimages to each other or taking them from the blockchain. Let's refresh and make sure we have no errors. Good, no errors. Then we need to do the same thing for victory. The JavaScript has to be able to detect that she got 3 in a row. So we do the same thing every time she reveals a preimage. We check if she has enough data to claim victory. And so that's what this code does right here. Same code as you've already seen. Also, I had found a mistake in it. I found a couple bugs in this code when I was making this yesterday, and one of them is here. If Alice proves that she won on the third turn, she could overwrite Bob in that turn. And this code lets her just take the money right away. But Bob has to be given a chance to say, no, 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 she overwrote me, right? So I need to change this at some point. So instead of just allowing her to unilaterally spend the money, it should send it to another address that like lets her take it after some time and give Bob an opportunity to prove that she committed fraud on her final turn. But I don't do that here, so there's a bug in the code, and we're just going to live with it because that's the way the cookie crumbles. All right, next is checking for fraud. So now Alice has functions by which she can automatically detect fraud, and so does Bob. However, we need to actually call them. So on every one of her turns, she will take whatever preimage Bob reveals and pass that as well as his previous preimages through the prove double turn function. And if it returns something, then she's going to construct a Bitcoin transaction right here that takes Bob's money. So that's what this does. It takes whatever step of the contract we're on, and if Bob cheats in that section, then it sends the money to the faucet. Of course, in reality, you'd want to change this out for one of Alice's real Bitcoin addresses, but here I'm just sending it to the faucet. And so if the function prove double turn returns true, it will give us a target and a script. It will actually assemble it'll assemble the script for us that we need Alice to use to spend the money, and it will hash it for us so that we can use it in a Bitcoin transaction. And then we sign this transaction and pop Bob's preimages into the witness stack, as well as the script that we got from prove double turn and the control block. And then we broadcast a transaction that takes the money. So that's what that does. And we do the same thing for the other two forms of fraud Bob can commit. So these other ones are the same code you've already seen, but now it's running whenever Alice detects. Alice runs this to detect whether Bob overwrote her, or Bob runs it to detect whether Alice overwrote him. So we just copy this. It does the same thing. If it detects that an overwrite happened, then it grabs the proof and creates a Bitcoin transaction, spending the money and giving it to the victim. So that's what that does. And then the last one for fraud is this guy. This is proving that they didn't overwrite themselves, but they overwrote their opponent. So if they do that, JavaScript will detect it, create a transaction, and then take the money, penalize the cheater or the person who's trying to cheat. So there we go. We have got all of the different ways for someone to cheat are now here, but only for Alice. We need to do the exact same thing for Bob. So It is all the exact same code, except all the variables are switched around, and sometimes Bob has like one fewer turn to do it in, so we have to change like a number. But I'm not going to explain all the code again, and also this is already too long, so we're just going to skip over that. But it's the same code as I just copy pasted and explained, or partially explained. Then we need to automatically detect if Alice or Bob gains a victory. So once again, this is the same code you've already seen, but now they're just checking if they won. So we pop that in, and Bob does the same thing. We've also got Bob checks victory in the same code block, and that should be good. Save, and I think that's it. We're almost there. I knew I would think I was almost done. So I wrote in a little thing to encourage myself as we're getting close to the end of this. Most of the logic is written, but we still need to actually have them take their turns. We have to like write code for it to have them press a button and take their turn. We have to have them wait for their turn. We have to display their moves, and we have to call all those methods we use to detect fraud or detect if you've won. So they're all pretty easy from here on. So this is Alice taking her turn, and I think the code also has Bob taking his turn in here. No, it's not. So I have to explain this one. So when Alice takes her turn, she picks a square, but before she does, she creates a transaction. She says, "Okay, on my turn, I'm going to take whatever address the money is in, and I'm going to say I want to spend this money. So I have to sign for that." She also says that the money is going to go into Bob's. She's going to pass the turn to Bob, so she needs Bob's co-signature for that. And then it's going to say, all right, now we need to know which preimage you're revealing, so we can detect which script to use to spend this money. So we alert her to place an X on the board. We wait for her to do, and then whichever one she clicks, we grab the corresponding preimage from her current move. So if it's her first turn, we'll grab 0 through 9. If it's her second turn, we'll grab 9 through 18, and so forth, all the way through her 45 different preimages. Then we will reset the game counter so that it is Bob's turn, and so that he can do it the same thing. Once we have her move, we grab the corresponding preimage from her current turn, and if it's 0, then we don't need a tap leaf guard, so we just set the Bob's preimage to nothing because we don't need one for turn 0. We get the corresponding control block she needs to make this move, and the script she needs, and the tap leaf she needs, and all of that stuff, and then she does it. We get her signature, we get Bob's signature. In a real BitVM application, you'd need to get this ahead of time. You'd need to get all of Bob's signatures ahead of time, moving the money into every address, and he would likewise need to get her signatures. But here it's not done yet, so I just have them do it on demand. And then we broadcast her transaction. We say, hey, it is now, your turn is done. Here's your transaction that lets you reveal your move, and then it'll be Bob's turn to check whether she committed fraud or to take his own turn, to make his own move. So Bob's turn is the exact same as Alice's, except likewise he only gets 4 turns instead of 5. So a few things are different. So let's see. There's Bob's turn right there. Save. But the code is the same, so I'm not going to explain it again. We're almost done. We're at 76 out of 88 or something like that. Then we just need them to wait their turn. So every time it's not your turn, you've got to have the little counter incrementing and waiting until your opponent makes their turn using wait a sec. So that's what this code does. Alice waits for Bob to reveal his accept preimage, which she can get from the blockchain. Also, if you can usually do BitVM applications off-chain, that's what it's designed for, so you don't have to do everything on the blockchain. So eventually, I'm working on a version of this where they just reveal the preimages to each other off-chain. But you still need to wait for them to do that and say, this is my move. So she waits for Bob to accept her move and then reveal his own move. And that's what those functions do. And then same for Bob. Bob has identical functions where he just waits for his turn. And he waits for Alice to move and Alice to reveal that she accepted whatever his previous move was. Last couple of things, we show the moves. This is just representing it in the console so that when the prompts are up there, we can actually see what's going on. So this code can probably be removed eventually because eventually the prompts will be gone, but not in the current state. So that just shows the moves in the console. And then we're basically done. All we have to do now is call all these functions we've created. And we do that in a series of 6 slides. All right. So this one calls Alice's turn as many times as she has a turn, so 5 times. And it calls Bob's turn 4 times, creating all of the addresses that encode the different ways that they can move, or prove fraud, or claim victory. Then it instructs them to send money to the initial address, which that should be done through a coin join so that this money's split up 50-50. But I'm not also going to do a workshop here on how to do coin joins, so this is where we're at. It asks us to provide the TXID, VOUT, and an amount. Normally, you'd get that from using an API to query the blockchain, but I'm doing it by just prompting them for it because it's easier. And I don't have to have even more code for API stuff. And then every time they take a turn, we create a transaction that spends the money to their opponent, gets their opponent's signature, and broadcasts their move. Says, hey, broadcast this to start Alice's turn. And actually, we can actually close this and see this working. Alice can take 1 turn now. So if we refresh our code with this thing here, we should be able to hit play, and Alice should be able to take her first turn. So it's asking us to send some money to this address. I'm just going to pretend that I did. I do 1, 2, 3, 4, 5, 6, 7, 8. Then I can copy paste that 4 times, and that's equivalent to a TXID. I'm just going to check that there's no errors in this thing, so we're not using a real TXID to actually send the money. And we'll pretend that VOUT0 has that uses that TXID, and we'll pretend we sent 10,000 sats. And yeah, she is able to start the game by broadcasting this. Of course, it's not valid, and so the game has begun. Like the first turn has been well. She hasn't picked a move, but she's ready to take her first turn. So let's do that. Let's call the function that lets her take her first turn by just copy pasting this right above where it says close this for now, but we'll keep adding to it. So we paste that right there. Alice can take her first turn. So this says we are on step 0 of the contract. That's where she's getting the money from, is from the first Bitcoin address that she sent money into, or that we sent money into. And her turn is turn 0, which is equivalent to turn 1, because we index the turns from 0. And the money is being sent from her address into Bob's address, Bob's first turn address, rather. And then we check if she won, which of course we don't really need to do that on the first turn because it's impossible to win on your first turn, but we do it anyway. Then Bob waits for Alice to be done. This number 9, so this is Bob's first turn, so there's a 0 here, and then the 0 and the 9 indicate which set of pre-images he's expecting for her to reveal. One of the set from 0 to 9. Then Bob checks fraud. This is on step 1 of the contract, and it is his turn 0. So every time we add a turn, we increment the step of the contract we're on, because the money flows through these 10 different Bitcoin addresses. So then Bob takes his turn, and we can just check if this works by doing this again, but not there. So if we hit play now, it'll ask us to fund Alice's address. 5, 6, 7, 8. And now it'll ask her to place an X, and then it'll ask us to reveal where she moved, and then it'll ask us to let Bob take a move. So Bob can place a move now. We'll have him move there. And it wants him to reveal this stuff to Alice. But yeah, we just keep doing that. We just keep doing that over and over again, calling their moves. So now we are down to this one. We do that 10 times, I think. 9 or 10 times. Paste it. And that is all of the moves they can make. So Alice's last turn is turn number 8, because we index from 0. So the 9th move is number 8. And her 5th turn is turn number 4. And then after the 9th turn, we just send the money back to the faucet. Really, if the 9th turn happens and no one has won, it should be a cat's eye, and they should get half the money and split it up. But here I'm just sending it back to the faucet because it's not done yet. And the last slide on here is just reveals the state of the game in the console and says, there's the game has ended. So we'll just do that right here. Save. And now we've got 1,500 lines of code. We can delete this little notice. 1,500 lines of code. And you, my friends, if you followed all the way through to this point, you should have written tic-tac-toe in BitVM and maybe even followed along with what we're doing. So let's try it. I'm going to send some money to this Bitcoin address, and it's not satisfying. So there's two ways we can satisfy this. Do you guys want to have somebody commit fraud and then have the other party win, or do you want to have a party win the game the natural way? Let's take a vote. You want to do fraud? Fraud? Okay, we got 3 for fraud, and that's what we're going to do. So everyone wants to see fraud. All right, so I got to send money to this address, paste it, and we'll open up the mempool. We want v out 0, happens to be the one we're using. V out 0, 10,000 sats. We got to broadcast Alice's transaction starting the game. So now the money is in that Bitcoin, in the first Bitcoin address, and she has 10 blocks to make her move. If she doesn't make a move within 10 blocks, Bob gets to take the money. So she will place an X. Well, where do you want to go? You want to go? Well, I'm not going to have a vote on that. We're going to go in the top left. So now she has to reveal this to Bob. There we go. It's Bob's turn. He can place an O. Do we want Bob to commit fraud, or do we want Alice to commit fraud? Just who gets the money? But it's all going to the faucet, so it doesn't really make a difference. All right, Bob, there's only one way Bob can currently commit fraud, which is by overwriting Alice. So we'll click it. It will warn us this is an illegal move. Your opponent will be able to take your money. So as soon as he does that, he has to broadcast his transaction, making that his move. And when he does, Alice can detect his move on the blockchain. So, no. What did I do wrong? I think I forgot to broadcast Alice's move. So here is Alice's move. Yeah, I forgot to do Alice's. So there's Alice's move. Now we'll do Bob's move, where he overwrites hers. Copy that, paste it, boom. His fraud is on the blockchain, and so she can grab his data from the blockchain. I should show that. Like, if I examine this transaction, I'm saying that she can get these 2 pre-images from the blockchain. So I want to show that. If we go to details, here they are. That's the move he's making. So you can see that right here. 1E7 is the move he's making. And 1829 is him acknowledging her move. So that's his acceptance of the move she made. And then down here, this is the pre-image she revealed in her turn. That is the tap leaf guard that forces him to accept her move. That way he can't just be like, I'm not going to acknowledge that you took the first square. He has to. It's the only way he can make a move. So he has to do all of that. All of those things are on the blockchain. Alice can get them from there. So we copy it, pretending she's getting it from the blockchain. And she also gets his move. And boom, it says, oh no, your opponent committed fraud. Check your console to penalize them and take their money. And we've got 2 versions of the transaction. There's 2 different ways that he could reveal the pre-images that are both valid. And rather than detecting which one it is, I just include 2 transactions where they're swapped, and then one of them will be valid. So let's try the first one, and we might get lucky and it's valid. Nope, that one's not valid. So they were in the other order. So we grab this one, and Alice is about to do a fraud proof. Well, you guys are about to do a fraud proof on Bitcoin. Boom. Alice proved fraud and took Bob's money because he overwrote her move and cheated in tic-tac-toe. Bitcoin can validate the rules of tic-tac-toe. And you can reuse this model to compute any logic. It doesn't have to be tic-tac-toe. Any challenge response protocol between 2 or more parties, you can encode in Bitcoin. And it's awesome. So there we go. That's the presentation. And we're supposed to do questions. Do we have time for questions? It is currently 11 o'clock and we started at 9:30, so it's been an hour and a half, I think. No, 2 hours and a half? How long have we been going? Probably too long. Are there any questions that I should answer? Really? This has only been an hour? That's not bad at all. Holy cow. We did a BitVM. We implemented BitVM, like application specific, but it's still BitVM in 1 hour and 20 minutes, guys. Yeah. Thanks so much. I'm going to stop the recording.